All right, so final video, I think, definitely just on the stuff she told us to study from this PDF. I'm going to go over this last section that's going to be on the exam, 8.3, the quotient group section. I gave it its own video because this stuff is just confusing. I was definitely very confused for a good while, so thought maybe I'd do a separate one if I wanted to just focus on this. So let's get to it. What is a quotient group? That's the all important question, right? Um, so we let H be a normal subgroup of G, and we let so G backslash H, you read that as G mod H. So H is normal subgroup of G. Let G mod H be the set of left cosets of H in G, and we define a binary operation as G mod H cross G mod H, giving G mod H by some AH BH equals ABH. Then we say G mod H with this binary operation is a group, namely the quotient group. That's the definition Quizlet gave me actually, so I thought it was solid, but uh, it's still confusing enough that I ended up defining it like 4 other times. So let's look at the next one. The quotient group, what is it? When you have a normal subgroup K of G, you can partition the cosets that make K, the cosets that K makes into a set. So this quotient group is a set of sets. The coset, it's a set of the sets that the cosets can be put into. Dr. C actually in class for the review today actually gave a pretty great analogy. You had a lovely bookshelf. The quotient group is the actual shelves on the bookshelf, not the books. The books are the cosets being partitioned, and G is the entire shelf itself. Clear. So, yeah. So these distinct cosets, and remember these cosets are distinct. They're in a set, and then they're in the set of the quotient group, meaning we partition G by K. We also can say, I put this on this card, but I have more definition cards, don't worry. Quotient group of G by K is the factor group of G partitioned by K. So that's not really a definition, but that was something I saw in one of her notes somewhere that I thought I'd write down. So if she said on the exam factor group, I might have a clue what that means. So quotient group of G by K is the factor group of G partitioned by K, which makes sense. The cosets are like the factors of G, and we group those into sets by K, and those grouped up sets are in one big set called the quotient group. Definition again. So writing it just in a different way. If N is a normal subgroup of G, then G mod N becomes a group, being the set of distinct right cosets of N in G. And I don't think I've said yet, but in order to have a quotient group, in order for the quotient group to even exist, you have to have N being a normal subgroup of G. If the group in question doesn't have a normal subgroup, there is no quotient group. Quotient group hack, if G is finite, then you can say the order of G mod N is the index of G to N. That's pretty lovely. Defining an operation on the set of right cosets of K and G, so it's a group. For A and C and G, the product of the coset KA and the coset KC is the coset KAC, i.e. KA times KC equals KAC. And for the additive notation, we had K plus A, K plus C, then the product of them is the adding. So put these in the parentheses. So that's the same thing as K plus A plus C. You don't have 2K here. 2K, like K is just kind of it's like a placeholder thing. You're not actually adding K, you're adding these coset things. But we want to make sure that this definition then, either additive or any other operation, that doesn't depend on the elements chosen to represent the various cosets, i.e. the poker chip activity that we did in class. So you need, like I said in the last slide, here, if you remember, we need K to be a normal subgroup of G for this to work. If K is not a normal subgroup of G, there is no quotient group. Defining this one more time, I think, for all K that are normal subgroups of G, we denote the set of right cosets of K and G by G mod K. Recall that right cosets are congruence classes. So this is what I'm talking about, that the quotient group is a set of sets, because a congruence class is basically a set of the equivalent elements. So right cosets are congruence classes, thus G mod K becomes a group under the binary operation that we just defined in the last slide. Ka times Kc equals Kac, or the additive notation, K plus A plus K plus C equals K plus A plus C. We know all this also by theorem 810. If NA equals NB and NC equals ND, then NAC equals NBD. Normality tells us automatically that AC BD inverse is an N. Theorem 812. For all K normal subgroups of G, the product Ka Kc equals Kac on G mod K are well defined. That is, if Ka equals Kb and Kc equals Kd, then Kac equals Kbd. Since, for example, Ka equals Kb implies that A is congruent to B mod K by theorem 8.2, all those years ago in the other section, right? Theorem 813. Let K be a normal subgroup of G. Then for G mod K, which is the set of Ka for all A and G, so that's the set of cosets, we have three things. G mod K is a group under the product Ka Kb equals Kab. If G is finite, then so is G mod K. I kind of said this earlier with that hack, right? If G is finite, then so is G mod K. And if G is finite, then the order of G mod K is the index of G to K, which is the order of G divided by order of A. So that's like an implication from Lagrange's theorem, since order of G is finite. And finally, if K is a normal subgroup of G, then for G mod K, we have that if G is abelian, then so is G mod K, since all subgroups of an abelian group are abelian. How would we prove that? Well, the first one, G mod K is a group under the product. We know the operation in G mod K is well defined by theorem 8.12, which was here. That was saying well defined. Oh. So this first part already done. The second one, if G is finite, then we have G mod K is finite, and we can quickly tell the order of it. You can prove using the for group. Oh, I think number 2, that goes with the first one. Maybe I should number this better. So G mod K is a group under the product. We know it's well defined by theorem 8.12, and we know it's non-empty. And then you prove it's a group with the 4 group axioms. For the hack with Lagrange's theorem, we just know that by Lagrange's theorem, since G is finite. And the last one, if G is abelian, so is G mod K. If G is abelian, then AB equals BA for all A and G. So that works for all the cosets. So G mod K is abelian only when G is abelian. How to actually find G mod K? It takes a long time. That's all I really have to say about it. Theorem 814, let N be a normal subgroup of G. Then G mod N is abelian if and only if AB times A inverse times B inverse is in N for all A, B, and G. And you can use theorem 8.2 and corollary 7.6 to prove that. Where theorem 8.2, let's go back. 8.2. Oof. I didn't think that'd be that far away. Theorem 8.2 is A is congruent to C mod K if and only if Ka equals Kc. And the corollary 7, oh gosh. Okay, so I tried to go all the way back to corollary 7.6, but that's actually from like the first exam, so it's kind of irrelevant. Just one of those known things. I'm pretty sure I just meant the like splitting up the like K times and stuff like that. So let's recall now before the next card. If G is a group, then its center Z of G is a normal subgroup of G. Especially if G is abelian, but it just kind of, yeah, that's a separate theorem, right? So remember we were like, oh, if G is abelian, then the center is always normal, and we were saying if G is a group, and the center of the group is normal. So this is kind of implied from the abelianness, but here this theorem's nice now just on its own because here we don't necessarily know that G is abelian. We just know G is a group. So theorem 815, if G is a group such that the quotient group G mod ZG is cyclic, then G is abelian. So that's an alternative way to figure out if G is abelian, which then is nice for like if G was mod 6, but you didn't know if G was abelian, you could use this to figure it out. Theorem 815, the proof of that, that's just kind of a little too complicated. I'm not going to talk that. Can apply those order rules we know from 8.1 to quotient groups as well. Example, order of G mod n is 4, then G mod n is isomorphic to Z4, or G mod n is isomorphic to Z2 cross Z2. So kind of what I just implied here. And that's it. Hooray!